Swayam Prabha. Digital India. Educated India.
So, good day to everybody. We are on lecture 3 in the course Geoenvironmental Engineering, and today we will cover waste-soil interaction. To briefly recapitulate, in lecture 1 we did introduction, we defined what is geoenvironmental engineering, and we said what is it that we will cover, the scope of the entire subject. And in the next lecture, that is lecture 2, we talked about sources and impact. That means what are the sources which are causing ground contamination and subsurface contamination, and how do we get an idea of the impact they make. And we said the larger the source, the shorter the pathway, and the greater the number of receptors, the greater is the impact from any waste disposal facility, be it solid waste disposal facility or a waste pond. So today we would like to talk about waste-soil interaction. And to begin with, I remember somebody asking me this question, is all waste hazardous? So we will first address that question today. So when you dispose waste on ground, this could be solid waste or liquid waste, it has to interact with the soil beneath it, and that's what we are going to cover today. And to begin with, we like to address the issue, what is hazardous waste, what is non-hazardous waste, and what is inert waste. So all waste is not hazardous. That means waste is rejected material. Waste is material which is of no use to us. If in the waste there is material which is of use to us, then we should reuse that material, and the rejects after the reuse of the material would then be waste. So I told this last time that hazardous waste is specifically listed by the regulatory authorities, and it's a huge list. It's not something which is 10 chemicals or 100 chemicals. It may be 1,000, and it is an ever expanding list. As man makes more and more complex compounds, these are not necessarily natural compounds which will be decaying with time or degrading with time. So we are having the list expanding. Once you have hazardous waste, if you mix anything with it, that also gets classified as hazardous. And if you take out anything from it, suppose you've got a large mound of waste, you say, all right, I will fractionate it, I will do screening, and I will take out the waste which is minus 10 mm sieve size. But this is waste which is derived from hazardous waste, and unless you can prove it otherwise, this will also be treated as hazardous waste. So there are, other than this, if you have a new material, then how do you say whether the waste is hazardous or not? So there are 4 tests: ignitability, corrosivity, reactivity, and toxicity. So these are standardized tests. These are written in codes of practice. So if you have a new type of waste, you will do these tests on it, and then there are limits which are prescribed which will tell you whether it is hazardous or not hazardous. So all these first 4 points cover hazardous waste. Now if a waste is not listed as hazardous, it is normally referred to as non-hazardous waste. If you suspect that this is a new material and it could be hazardous, then you are supposed to do these ignitability, corrosivity, reactivity, and toxicity tests. But otherwise it would be treated as non-hazardous. So municipal solid waste, for example, does not come under the list of hazardous waste. So it is treated as non-hazardous. Non-hazardous does not mean inert. Non-hazardous does not mean that it will not contaminate. Hazardous means it is proven to be harmful to health. There is a direct link between the waste or the contaminant inside the waste and human health and its impact on the ecosystem. Non-hazardous means that there is no direct link. There is no direct link. However, the constituents can accumulate and the concentrations of the contaminant can increase because of accumulation. And finally, you may have something coming out which is above the acceptable limit. Let me take an example. Ash. In the fields we spread ash. We burn wood. If you look at the farmers in their stoves, they'll burn the wood and they will spread the ash on the ground because you find that it helps the growth of the next crop. But if the same ash is now accumulated in a mound which is 10 meters high, at the same place, it may have a different effect. It may have some deleterious salts which with water would come down, and because it is 10 meters thick, as it comes down, there will be an accumulation. And those accumulated salts, which were earlier within the limits, would now be exceeding the permissible limits and it can cause contamination. Construction and demolition waste is often referred to as inert waste. Now, inert waste is something which is, in its purest definition, should not be chemically active, should not be biologically active, and should not be physically active. The three things you need to have to become an inert waste. Again, I say, not chemically active, not biologically active, and not physically active. Now, construction and demolition waste is all that we are breaking down, right? And if we are breaking down a building, then it's concrete, it's brick, but it is also wires, it's also the paint, it's all the rebars, the reinforcement bars. So, untreated C&D waste or unprocessed construction and demolition waste is definitely not inert, right? Then the next step is you can process the waste and remove. You can do magnetic separation to remove the metals. You can do other kinds of separations to remove some of the other constituents. Then you get what is called processed construction and demolition waste. It's difficult to remove paint from it, and paint itself has some properties which are bothersome. So still it is not inert waste. However, if I was to completely take a brick and crush it, then I might be tempted to say that this brick was produced by a process of baking and it's nicely burnt, it is made from soil, so maybe it is inert. But crushed material is not physically inert. If you crush something, you get dust out of it, you get suspended solids out of it. So the term inert, which we seem to suggest that it should not be chemically and biologically active, should also include that it is not physically active. And that's a rare waste to get. Almost all natural materials undergo erosion. The only ones which are not going to undergo erosion in our, what is the design life of our facilities? 50 to 100 years. So maybe some of the things which will not undergo erosion in 50 to 100 years will be boulders and rocks. They will remain for 50 to 100 years wherever they were. And maybe physical and chemical weathering will take much longer, thousands of years or more. So maybe they can be termed as inert, but really otherwise calling C&D waste as inert waste is a misnomer. So the question is, we know that hazardous wastes cause contamination because there's a direct link. If any contaminant comes, do non-hazardous wastes cause contamination? That's the next question. do non-hazardous wastes cause contamination? And we'll look at 3 examples toward the end of this lecture. The first example is I'm going to put common salt on ground. Is common salt hazardous? Sodium chloride? We eat it. It's not classified as hazardous. So if I take 100 tons of common salt and put it on the ground, what happens? We will examine it at the end. Mining overburden, we talked. It's just excavated soil and rock. It's termed as inert, again a misnomer sometimes, but nevertheless, does it cause contamination? I take clean water in a pond. I create a pond by making an embankment and I store clean water in a pond above the ground level. The water is clean, so it's non-hazardous. The material you have made the pond of is embankments of natural soil. Is it contaminating the ground? We will look at these 3 questions towards the end of this lecture. So let's understand that I've been drawing this diagram almost every day. I put some waste. On the ground. When I put waste on the ground, solid or liquid, it becomes a part of the hydrological cycle, unless I have designed it not to become a part of the hydrological cycle. You can't do anything about it, which means you put out waste in the open and rain will fall on it. So if the waste was not there, where is the rainwater going? It's becoming surface runoff, and partly it is recharging the groundwater. Is that right? So when rain falls on the ground, bulk of it recharges the groundwater, or bulk of it is surface runoff. So a bulk of the rain which falls on the ground doesn't go into the ground, because the ground normally has grass or has a natural slope. So infiltration into the ground is low. Most of it is surface runoff. It goes to a local drain. The local drain goes to a river. The river goes to the ocean. And therefore, the water goes like this, and maybe some of it goes like this. And what happens? This goes to the ocean. Then what happens? It evaporates. It becomes clouds. It comes back and rains again. So really, the hydrological cycle is so every now and then we have monsoons. Where are the monsoons coming from? The moisture-laden clouds. Where is the moisture coming from? Some place where the water evaporated, and when that cloud comes to a cold region, it falls rainfall. So this cycle is going on every year, and our waste has knowingly or unknowingly become a part of this cycle. It chalta rahega. Right? So we are looking at waste-soil interaction. And the first important thing to realize is when we place something in the open, we are making it a part of the hydrological cycle. If we had if I had placed the waste in a shed which had a proper roof and walls and was closed all around, then what would happen? Then the waste would not become a part of the hydrological cycle, because the rain would fall on the roof would put the rainwater aside, and we would prevent this waste from becoming a part of the hydrological cycle. But till the time that happens, we are looking at this phenomenon. We are looking at the phenomenon of some waste being on the ground, rain falling on it, rain percolating through it, and going into the groundwater. So I've used some terminologies which you might be aware of: vadose zone, saturated zone, capillary rise, but we'll take a quick recap on this. What we want to know is, in waste-soil interaction, what is happening when the water passes through the waste? And what is happening when it passes through the vadose zone? And what is happening when it is into the saturated zone? That's what we want to really know. So just let's quickly go back to those definitions. Saturated soil is all voids filled with water. below the groundwater table is saturated soil. Above the groundwater table, saturated or unsaturated? Partially saturated or unsaturated, but unsaturated soil, voids filled partly with water. And the pressure head inside is negative because of surface tension effects, so you have a suction or a negative pressure in the partially saturated soil. But there is a capillary zone above the groundwater. Is that saturated? Yeah, the capillary zone is saturated, but the pressure inside the capillary zone is negative because the capillary action is making the capillary rise. So the vadose zone, the word vadose zone which we have used, it covers both the unsaturated soil and the capillary rise and the capillary zone. Truly, the saturated zone is below the water table. So phreatic zone is the zone beneath the water table. Now we start to get positive pore water pressure, and groundwater flows in the saturated zone under total hydraulic head from higher level to lower level. This is called advective flow. We've all done this. The Darcy's law is valid. Q is equal to KIA. That is the mechanism by which the water is flowing in the saturated zone. We have not done how the water flows in the unsaturated zone. I will briefly visit that here. The other mechanisms, once the groundwater is contaminated with something, that means the concentration in the groundwater of a particular constituent, the concentration of a particular constituent in the leachate is higher than in the groundwater. So there's a concentration gradient. So over and above the advective flow, you have the other mechanisms which are diffusion and dispersion. We'll discuss them very briefly later. This is not a course on groundwater contamination transport. These are processes. There are huge softwares which can simulate diffusion and dispersion. Ours is a course on design of waste containment facilities, design of slurry ponds, and remediating contaminated sites. So let's look at the process. The rainwater falls on the waste, some runs off, some infiltrates. So how much will run off and how much will infiltrate will depend on how the waste has been placed. If the waste is properly compacted, it has a convex upward shape, it has got a layer of soil on it, then most of the water which will fall will run off on the convex shape. However, if it is a waste dump which nobody is managing and the surface is like that, undulating surface, then the water tends to stick on that undulating surface. It will form small puddles, and that water tends to go down more. So rainwater falls on the waste, some runs off, some infiltrates. This infiltrating water, will it reach the ground? My question is, some water enters the waste. Will it reach the ground? So let me go back to the slide and let's try and simulate this on the board. As I said, some will run off and some will infiltrate. So if 10 units fell, if 10 units of rain fell, and let us say 7 units ran off, that means a good convex shaped thing, then 3 units went in. And now will the 3 units reach the ground surface? That's the first question. Pardon? No, there's no lining. This is just a waste dump. It's just a waste dump which seems to have a convex shape. If it doesn't have a convex shape, 3 will run off, 7 will come in. Right? The question I'm asking is, if 7 units were here, will there be 7 units here? Because where will they vanish? Decomposition of what? Of H2O?
Chemical reaction inside.
Well, let it chemically react. So what? Some material will go into solution and still come down. So first, let's assume that the waste is not reactive. Then will all the water which fell on top come down?
Maybe it will get fill up the void, some part of it.
So it will fill up the void, then it will come down. So what you're trying to articulate is that if the waste is inert and X units went in, some may be held by the pore space. I'm not sure. whether it will be held or not. But if you have fine pores, then by capillary action alone you will hold water. Only excess water will come down. So if X units come in here, something less or more than X can come. How will it be more? Maybe the waste itself is also squeezing out liquid. If you take municipal solid waste, put it in a plastic bag and just hang it like that, after some time, जैसे डस्टबिन के नीचे आपका पानी आ जाता है ना, तो क्या है वो squeeze, that's the squeezed water or the decomposition water which is coming down. So the X is not going to be equal to the Y which reaches the ground, and if it is inert, what will reach the ground will be less than X, because some water will be held in the matrix of the pores and balance will reach here. Now if it is, I said this is if the waste is inert, but if it is a waste which is not inert, then chemical reactions will also take place as the water goes down. Mostly there will be dissolution, some salts will dissolve and form a solution, but there can be all kinds. Water will cause biodegradation, it may be anaerobic, it may be aerobic, so all kinds of complex interactions can take place as the water goes down. So rainwater becomes leachate and it reaches the bottom. But if leachate is going to be held in the pores, you may have less water reaching the base than the water which was coming in from the top. Then what happens? Now our leachate encounters the soil. Now in the soil also there is a distinctly saturated zone and the unsaturated zone. So when the leachate goes into the soil, what will happen? Again some of it will be held, because the unsaturated zone, maybe there is dry soil, so you add 1-2% of water, it is not going to flow, it is going to be held because there is a field capacity of the soil. Then the excess water will come down. The other thing is, will there be a chemical reaction now between the soil and the leachate which is coming in? What do you think? Maybe? Yeah. So intense interaction between the water and the waste, and it can be two-way. It may be dissolving something and going down and precipitating it at a lower level. We can't predict the complexities of this, but we can model them. Then you hit the soil, and is soil inert? Why not? Is sand inert? Well, let's not talk about physically inert, but is it chemically and biologically inert? Soil? Sand? So you said soil may not be inert, but sand may be inert. Is that a correct statement? Why will soil not be inert? It's a mixture of? What is typical organic content of soil? Now you only started the discussion that so what was said was soil is not inert because it is a mixture of organic and inorganic. So typically if I take a soil, when you do soil mechanics, is organic content a normal test which you do? Yes or no? No, because why? Organic content is very high or very low? Very low. So on the surface of the soil, for the agronomist and the agricultural engineers, there is plant growth, there are roots. So let's say for the first half a meter, you will have organic content because of biological activities. So you're right, there could be biological activities, but do you think you'll have biological activities 10 meters below the ground? No, maybe there'll be some microorganisms who can live without oxygen. I haven't done it, but the organic content of soil will normally not be more than how much? 0.5%, 1%, maybe less than that. So the organic content of soil is typically very low, but there are a lot of microorganisms in the soil, typically in the upper zone. So if there is sand, pure sand, will there be grass on it? Unlikely, because pure sand does not promote growth of grass. You have to have silt in it, which will hold the water, which will hold the nutrients, will allow the root growth to take place. So, sand and gravel, so typically gravel is easier to understand than sand. Gravel is definitely not going to have any interactive properties, both biologically and chemically, mostly. So when the leachate hits the ground, and most of the soil is not pure sand and pure gravel, it will be silty sand, sandy silt like Delhi, so there is grass which is growing on it, so it is active. And if you have clay silt, silty clay, that will be active. Clay particles are inert. Why are they not inert? Clay particles have a net negative charge. So they are electrically a lot of negative charge on the surface of clay particles. So they are totally different from sand. In any case, leachate will interact with the soil. Even if the sand grains are inert, there may be some interaction of precipitation from the water onto the sand grains. Suppose a solution is coming down the waste and it is picking up chlorides or carbonates. When it comes to the soil, it suddenly becomes supersaturated with respect to chlorides and carbonates. Different pore size, different environment altogether. It might want to, well, the temperature changes, right? Maybe the municipal solid waste had a temperature of 40 degrees and the soil had a temperature of 15 degrees. So maybe what was solubility at 40 degrees was high and at 15 degrees is low, so something will come out of solution. You may have inert grains. So there is interaction between the leachate and the soil. And the balanced leachate, which is over and above the holding capacity of the soil, goes into the groundwater. And that interaction continues because there is a soil matrix in the groundwater also. But now the groundwater is moving. This moisture, nothing is moving here. But when you come to the groundwater, it is moving under a hydraulic head from higher ground to lower ground. So consequently, the contaminant begins to move in the groundwater. So that is the process. That is the process. At every stage there is interaction and all kinds of interaction. So for a civil engineer, it is boggling. It's mind-boggling, but it's very simple. It's too complex. So, and what is the worst design condition? Worst design condition is leachate is coming into the waste. The leachate is going into the soil is becoming saturated, and then it is getting a saturated connect with the groundwater. That's the worst condition, because partially saturated soil, the permeability of partially saturated or unsaturated soil is more than of saturated soil or less than of saturated soil. Why less? Void space to same hai. Yeah, so one is the issue of matrix suction, and second, water will only travel through the water film. So if you have a void space in which 50% of it is water, then water will only travel through that water film, and therefore the pathway, the cross-sectional area is slower. So partially saturated soil will have low permeability to water. As saturation increases, permeability to water will increase, and when it is saturated, it will become the highest value. So critical design condition is everything is saturated. So we make this building is made for its self-weight, but it's made for critical design loads, which is what? Earthquake, wind, tsunami, cyclone. So similarly, when you design something for waste, it is for the critical condition. It is not for the intermediate condition, right? So let's summarize what we've talked about. The process, rainwater falls on waste, some runs off, some infiltrates. Some infiltrating water is held by the waste. Some goes back by evapotranspiration. So water is going down, but it's also going back by evapotranspiration. Excess water moves down. This excess water interacts with the active contaminants and carries them down as leachate. Leachate infiltrates the soil. Some leachate is held by the soil. Excess moves down. Some contaminants are attenuated by the soil. Attenuated means they retard the some of the contaminants are held by the soil. Concept of rapid sand filter. Your leachate will interact with the soil, and maybe the net negative charge of the clay particles will hold back calcium Ca2 plus ions. So that is called attenuation or retardation. Leachate with attenuated contaminants reaches the groundwater and then flows with the groundwater. But the interaction continues in the groundwater with the soil. So what kind of interaction occurs? There is physical interaction. As the rainwater goes down in a waste dump, total suspended solids may go down. The fines may travel with the water as it goes down. So there is a tendency, if you have heterogeneous municipal solid waste, the fines tend to come down with time, because as the water goes through with it, the fines come down with it. And there are a lot of chemical and biological interactions: ion exchange, reaction, sorption, desorption, dissolution, precipitation, volatilization, biodegradation, and others. Lots of, I can't predict what is going to happen, which is the predominant reaction which is going to take place. And these are affected by the temperature, the pH, the presence of oxygen or the lack of oxygen, the moisture content in situ, and other factors. So this whole thing is like a biochemical factory. Which is going on. And that is, waste first interacts with the water then interacts with the soil, and then it reaches the groundwater. Again, one may tend to think, let us say I have soil. Okay, let's go to original ground. And 100 units of rain are falling on this original ground. And let us say out of these 100 units, 50 units run off. 50 to 60 units are running off, surface runoff. Then what is going down? 40 to 50. Now this will be held, some of it will be held, right? Because the soil on the ground surface is dry. The water table is somewhere deep below, or few meters below. So out of this 40 to 50, due to evapotranspiration, 20 to 30 may go up. So what is going down? Even 10. So maybe, now these are all hypothetical figures. But if you look at India as a whole and take the major river basins, the following is what is observed. That about 40% of all the rain goes to the river streams. It becomes stream flow. 40 to 50% becomes stream flow. Groundwater recharge is only 10% or less. So groundwater recharge from directly precipitating rain is not very high. And the balance is evaporation and evapotranspiration. First, what accumulates on the surface is evaporated, and then the plant roots also take it out. So very little amount reaches. But if I put a waste dump now in position for you, a badly maintained waste dump, what is happening? The 50 to 60 falls to 10 to 20 or 20 to 30, right? $80 goes in. Now in a waste dump there are no grass growing or vegetation growing. It's a municipal solid waste dump, or it's a hazardous waste dump. So what happens? Is there transpiration? Root? No. Is there evaporation? Yes. If some of the water holds on the top, it will evaporate back. So maybe 10 will go back. 70 is still going through. Now comes the model into play. Out of the 70, maybe 30 should be held by the waste. Maybe. But what if the waste has preferential flow channels, vertical preferential flow channels? If you sometimes go to a waste dump, you'll see vertical cracks. So what happens? Through that, it will go very fast. It will go very fast. So this whole concept that this is a homogeneous soil mass doesn't exist for waste. Waste is a heterogeneous soil mass. So if it was to go uniformly everywhere, then maybe 30 to 40 would be held back. But it doesn't, and you may have vertical paths and you may have horizontal. I mean, any kind of high permeability zones. And then it comes and sits at the ground surface, and the ground surface is horizontal. Waste is typically placed where? In horizontal ground or low-lying areas? I told you, most of the time waste is put to start with in a low-lying area. So low-lying area means that you had so all the thing will come and accumulate in that low-lying area, and the fines have come down anyways. So, and will this go back up? No. There's no evaporation possible, it's all covered. So a larger amount of leachate tends to come down. However, if you start doing calculations in the leachate by using the holding capacity of soil or equivalent soil mass, you tend to show a lot of water is held in the waste, which may get held or which may not, depending on the vertical preferential flow paths. And if you go to a waste dump, you'll find perched water tables. Why? Fines came down and settled at one level. Fines came down and settled at another level. So there may be high permeability zones and there may be impervious zones as well. So when you are excavating, though you know that there is no water table, but you find little puddles of water inside the waste because fines are coming down. They don't reach the base. When you have a 30-meter high dump, fines will come down. 10-meter level पे कुछ बन गया artificial, वहाँ पे fines इकट्ठे हो जाएंगे. Then on that the perched water table will form. So when the leachate accumulates here, it will stay there because it's a low-lying area. It doesn't go back because it's covered. The sunlight is not reaching it, it's not going to evaporate back, and there's no evapotranspiration which is going to take place. The contaminants come. The contaminants interact here, they also interact here. The water is moving in this direction, the groundwater, so a contaminant plume is formed. And this contaminant plume travels in the direction of flow of the groundwater. So, infiltration, entry of water made available at the ground surface into the soil, that's the terminology, drawn back by evaporation or transpiration by the roots. After it is drawn back, redistribution of water content to replenish the soil moisture deficit. You have the moisture inside the soil, natural moisture content. And then you have the field capacity, that is the moisture content beyond which water will flow down. So the difference between the field capacity and the natural water content is the soil moisture deficit. So if there is a deficit, the water will continue to be held. Only when it is more than that will it go down. Then you may discharge to nearby surface water or you may recharge the groundwater. In fact, this should be up. You may recharge the groundwater and the groundwater may discharge into the nearby surface water. Should I quickly change it? Yeah, discharge to nearby surface water. There are some terminologies, I just want you to quickly brush them. You might have done them, we've all done them at the undergraduate level. Infiltration rate, volume of water flowing down into the soil per unit ground surface area per unit time. And infiltration capacity, if you flood the surface of the ground, what is the maximum rate at which infiltration will take place? So it says volume of water flowing down into the soil per unit ground surface area. And infiltration capacity don't seem to want to. Anyways, infiltration capacity is the maximum infiltration rate. Field capacity, as I told you, moisture content of unsaturated soil above which rapid downward movement of water takes place, and soil moisture deficit, moisture content below field capacity. A soil with deficit holds infiltrating water. We all know about flow in soils, Darcy's law, advective flow, but let's recapitulate. The ease with which water flows through the porous media is reflected by the term permeability. You will also find the term hydraulic conductivity written in many books. So flow in saturated media is through difference in total head. Flow in unsaturated soil will not occur unless suction greater than the tension is applied. If the water is in tension, you have to have a head greater than that. So typically in dry soils, the tension is the main dominating factor. As saturation increases, tension decreases, and at saturation gravity flow occurs. K of the unsaturated, we already said permeability of the unsaturated is less than the permeability of the saturated. Water movement is only through the liquid phase, that is within the water film around the particles. As saturation increases, volume of water film increases, hence hydraulic conductivity or permeability goes up. The main mechanism is advective flow. That means when I look at the plume is moving because of the difference in the, it's a gravity flow, and there's a difference in the total head causing flow from one point to another. The other factors are diffusive flow, which is due to difference in concentration, which we look at when we are doing contaminated sites, what is diffusive flow, and dispersive flow, due to variations in pore size and hence variations in seepage velocity. You send a water along a channel and suddenly the pore sizes change. So there will be dispersion in the flow because of the fact that there is a kind of a tortuosity. The seepage velocity in the fine pore will increase. So it's not the same thing as everything traveling along one line, and that is the dispersive flow. In coarse-grained soils, advection predominates. It's more than diffusion by many orders of magnitude. So diffusive flow and dispersive flow are not of any consequence. It may be 100 to 1,000 to 10,000 times larger. Advective flow, that means flow under gravity. Why? Because the coefficient of permeability is very high. In clays with low permeability, sometimes diffusion can also become significant. So by and large in soils, diffusion is very small. But in clays, diffusion can be of the same order of magnitude, and this can become important when we see performance of liners. When we see performance of liners, this can become somewhat important. Flow in rocks is different from flow in soils. Soils are typically treated as homogeneous, isotropic, though horizontal permeability in soils is usually larger than the vertical permeability because of the depositional effect. So if you have alluvial soils will deposit in layers, and there will be some anisotropy, and horizontal permeability of alluvial soils may be more than the vertical permeability. But in rock, it's all about fissures and joints and fractures. So mostly, if you have solid rock, flow is not going to take place. But if you have fissures and joints, flow will take place. And it is highly determined by the direction of the fissures in the joints. It's highly determined by the direction of the fissures in the joints. And even in the unsaturated zone, you may have flow occurring along these fissures and joints in a particular direction. The surrounding environment may be all unsaturated, but the water may travel through a connecting fissures and joints. So it could be vertically downwards, it could be horizontal, it could be inclined. So it's highly directional. And that's the difference, that in soils you have a granular media which is porous but which is by and large uniform. In rocks you will have so you can have preferential flow paths in these joints and fissures. So you may have flow taking place very fast. And many of the contaminated sites is because the waste was dumped on exposed fractured rocks. When you have rock, typically the ground surface will be more inclined. That means the gradient is higher, and water will travel during the rains through these fissures, and if the contaminant has entered, it will travel very fast and reach a well in a particular direction. So rocks are all governed by the fractures and fissures. Let's look at flow regimes. Let me see if I can use the projector. So I'm just going to introduce you to the issue or the concept of recharge and discharge. So if this is the topography of an area, water is reaching a stream or a river or a rivulet, and that's the ground surface topography. So what happens when rain occurs? This is high ground, this is low ground. So this is the watershed. On both sides the water is coming in. So if I have rain here, what will happen? It's simple for me to say that whatever rain falls here, it's going to go down. A little bit may come here. Okay? But what happens here? It might you might have a small puddle or a pond, or you may have a minor rivulet. So this will then work to recharge. Okay? And finally, all this water will go and discharge into the river. So any ground will have recharge zones and discharge zones, and bulk of the area is recharge. Small amount is discharge. See, this is the discharge area for groundwater, and this is the recharge area for the groundwater. If I was to attempt to make a rock line, I just gave you a ground surface. So maybe the rock is different ways, but one of the options is maybe the rock is like that. So all this may be a deposited material. So you have rock, you have groundwater, and all this groundwater is recharging the groundwater. And so depending on where you put your waste now, you can have a problem of the appropriate nature. For example, if you put your waste in this low-lying area, you have created a real problem. Why? Because this is a low-lying area and it is recharging the groundwater at that location. So let's go back to the slide to reinforce the the watershed is the area from which water flows to the river basin. I showed you a watershed, one half of it. Groundwater recharge areas predominant, groundwater discharge areas are low. Flow paths are from the recharge to the discharge. How is the groundwater flow taking place? From the recharge to the discharge area. And a set of flow paths give you a flow regime. And in this flow paths, you can have an aquifer, which can sustain a water supply, or you can have an aquitard. That means the permeability is not high enough to sustain water supply. Quickly, as we have already discussed this, soil has ability to interact geochemically with the constituents of leachate and groundwater. Interaction can cause immobilization or retardation of these constituents, and this is referred to as geochemical attenuation of the soil. Attenuation capacity is not infinite, but it is limited. Please understand this. There is an initial attenuation capacity which is high, right? But what will happen? After some time, whatever had to deposit would have deposited, and the attenuation capacity will go down. So initial attenuation capacity looks very attractive, that soils can withhold contaminants from reaching the groundwater. But if leachate is coming in every year after year after year, there is not going to be infinite capacity. So in the long term, the attenuation capacity depletes. All constituents are not attenuated. Don't think every contaminant will get contaminated. Typically, for example, a chloride ion is Cl negative and a calcium ion is Ca2 plus. What will happen? Ca2 plus can be retarded by clay because it might get attached to the net negative charge on the clay. But what will happen to chloride? Cl minus is not going to be retarded. So many things will get retarded, many will not. So there are, if you look at literature, many examples of chromium, arsenic, cyanide, selenium being retarded in many soils, but not infinitely. They retard for some time and then a breakthrough occurs and it goes forward. So which type of soil exhibits more geochemical interaction? Yeah, so between coarse-grained soils and fine-grained soils are more geochemically interactive because of the net negative charges on the surfaces, also because of the finer pore size and more intimate contact of the surface area with the leachate. Can we measure attenuation? Well, you can do some laboratory tests. First, of course, you can do the mineralogical and geochemical properties of the soil. If you have larger clay content, you can say it will have larger geochemical attenuation capacity. But the simplest test is take some leachate, put some soil in it, mix the two in some proportion, leave it for 24 or 48 hours, come back, take out the leachate and see whether any chemical has depleted. If the concentration has gone down, that constituent is being retarded. In sequential batch testing, you do this more often. Means you take a leachate, you interact it with some soil, then take some fresh soil, interact the balanced leachate with that, and in this way you can get a cumulative figure. So you can get single batch testing will give you a kind of initial attenuation capacity, and sequential batch testing will give you a more cumulative attenuation capacity. You can read about these details in the chapter on geochemistry in Daniel's, the first book that we had talked about. Percolation is real life. That means take a permeameter, a falling head permeameter, and percolate the water top to down. So you put a leachate at the top and take it out at the bottom. This is a kind of a column test. Initially the attenuation capacity will be high, then gradually the attenuation capacity will deplete. So we can do laboratory tests to get an idea of attenuation, and we can also do field testing similar to a field permeability test to understand attenuation. So attenuation capacity is typically mass of the contaminant removed over the mass of the soil. And this is again a function of many things: the throughput, the time, the concentration, the temperature, the available oxygen, the pH. But you get a value, you get a hold on the value. From design perspective, attenuation is overrated. I would like to design assuming the attenuation capacity is depleted. I cannot rely that the soil will attenuate, unless you can tell me, sir, no, I have got 30-40 meters thick soil which will attenuate the leachate and show that for the next 100 years it can attenuate all the contaminants which are going to go down. So typically, geotechnical design presumes attenuation capacity is depleted. We should not let anything go into the soil. Because of this attenuation, and everything doesn't get depleted, as I told you, we find that in the plume there are 3 zones: a core zone, an active zone, and a neutralized zone. In the core zone, attenuation capacity is depleted. In the active zone, interaction is taking place. And in the neutralized zone, conservative constituents means non-reactive constituents. I gave you the example of chlorides. So it may be a non-reactive constituent. So in the neutralized zone, the non-reactive constituent will go forward. Just imagine a plume. What will be in the front of the plume? The reactive components or the non-reactive? If I have a plume which is traveling downstream along the groundwater flow, in the very front of the plume, what will you get? Reactive constituents or non-reactive? Non-reactive, because they have escaped all the reactions. The reactive components are coming only when the attenuation capacity will get depleted. So really, the non-reactive constituents travel the fastest. And if you are trying to detect groundwater contamination, what is it that you should be looking for? Yeah, suppose you have 5 or 7 contaminants, you are trying to find out what is the spread of contamination. So you should actually be targeting the non-reactive contaminants. So that was the plume that we had seen, and those are the 3 zones. That's the core zone. It's completely depleted. Attenuation capacity is completely depleted. Very little contaminants are held. Here, attenuation capacity is there. Reactions are taking place, right? And here, the reactive constituents have not reached. Only the neutralized conservative constituents have reached. So here you will find the non-reactive contaminants. And as I said, if you are putting a tube well to detect, or if you are using other techniques, you are trying to going to detect the non-conservative. So core, active, neutralized. So the critical design, I've already stated this is just reinforcing. We assume accumulation of leachate at the base of the waste because it's a low-lying area. So there's a kind of a continuous supply of leachate, either from the squeezing fluid of the waste or from the rain water which has infiltrated. We assume that the Vadose zone is saturated, and we assume that the attenuation capacity is depleted. And our solution must be a design which takes this into account. Finally, we have still to discuss these 3 examples. So let us examine whether common salt, when it is stored on ground, should be treated as hazardous, non-hazardous, or inert. Common salt is not inert because it dissolves in water. So when rain will come, common salt will dissolve in water and tend to percolate in the ground. Common salt is not classified as a hazardous material because we eat it, and in low concentrations it is not harmful to man. However, if common salt percolates into the ground and reaches the groundwater table, it can cause drinking water to become like salt water and not suitable for drinking purposes. Consequently, common salt for the purpose of subsurface contamination can be treated as being harmful to human health. And thus, depending on the system that we choose, we can either designate it as hazardous because excessive intake of common salt can cause high blood pressure in human beings, or we can also call it non-hazardous like municipal solid waste, which means though it may not directly impact the health in low concentrations, it however renders drinking groundwater not suitable for drinking and thus needs a liner or a protective measure to prevent the salt from contaminating the groundwater. And the system that would be most suitable would be basically a liner which we use for hazardous waste material, because we would not even like even a drop of water having salt going to the groundwater and spoiling the quality of groundwater. So what this demonstrates is that depending on the way you look at a particular contaminant or a particular constituent, you may treat it as hazardous or non-hazardous, and even though we eat that constituent such as common salt, its percolation into the ground can have disastrous effect on the quality of groundwater. So we have to be careful about protecting our subsurface groundwater resources. Mining overburden, which is nothing but excavated soil and rock, appears to be material which is inert, and therefore one is tempted to classify it as inert waste. However, please do recall that excavated soil or rock is prone to erosion both by wind and by water. So during hot dry months you will have fugitive dust emissions from mining overburden, and during monsoons you will have erosion gullies being formed on the mining overburden and muddy water going into the rivers. So mining overburden is not inert. It is physically active and it impacts the environment in the form of fugitive dust or total suspended solids. So mining overburden too can be classified similar to municipal solid waste, that is a non-hazardous waste which will impact surface water and air quality around the waste. Clean water in a pond. Well, clean water is drinking water, and if it percolates into the ground, it can reach the groundwater. However, since it is drinking water, it is not likely to alter groundwater quality. However, if a lot of clean water is stored in a pond in an area which did not have a pond in the past, the water may cause the groundwater table to rise. As the groundwater table rises, it can have two impacts. One, the area or the land can become waterlogged, or two, salts from the lower strata of soil can come up to near the ground surface as the water table rises, and this can affect the vegetation or the crops which are growing at the ground surface. So once again, it is important to recognize that clean water may not affect quality, but it can change the ecosystem, because both waterlogging as well as upward movement of salts can affect the quality of vegetation and the quality of the crops which are growing on land adjacent to the pond. And hence, one has to be careful that we should line the pond with an impermeable material so that the water does not go into the groundwater and cause a change in the groundwater regime. So, have a good day. All the best.